last lesson I had asked the people to compare the current in three very simple circuits. The one circuit had just a battery and a bulb connected. The other circuit had two bulbs connected in series, and the other one had the two bulbs connected in parallel. All of these were are supposed to be identical, bulbs and battery. And I asked you to see if you can figure out how the currents, the different currents involved in these three circuits compare. This very simple question actually is very important and determines, I can tell whether you have a good understanding of what is going on in series and parallel connections. So, so I prepared a worksheet here. Let's see if we can go through these questions one at a time. But I also want you to think of these questions by yourselves. So the first question says, what happens to the brightness of bulb B1 if you connect a second identical bulb B2, first in series, like in this first circuit, and then in parallel? So we begin by comparing the brightness of the bulbs. Okay. If we compare the brightness of bulb B1 here in this circuit where it is alone connected to the battery, and in this scenario where it is connected in series to another bulb. So if we compare the brightness of those two bulbs together, what are we going to see? The bulb B1 we expect to glow dimmer, and I wish that you could send me messages on what you think will happen. So the answer is that B1 will glow a lot dimmer than the bulb B1 in the first circuit. Next, in this circuit now, where the two bulbs are in parallel to one another, I would like you to tell me, if you compare the brightness of B1 here in these two circuits, circuit A and circuit B, how does the brightness of those two bulbs B1 compare in the two circuits? Can you please take like a few seconds to tell me whether which one is brighter, or whether they are the same in brightness, they bright equally, or what? I'll wait for a few seconds until you answer here. So you say B1 in A will be brighter? The answer is no. The brightness of the two bulbs will be exactly the same. So B1 glows with exactly the same brightness in this circuit where it is connected in parallel to another bulb. And in fact, now this tells me that perhaps you don't understand, which is very common. We don't understand well what's happening in a parallel connection of components. I want you to understand the parallel connection as if we have like two bulbs separate. One bulb is connected across a battery, and then we take another bulb, identical bulb, and we connect it in its own circuit, but across the same battery. As if we have, in other words, two separate circuits connected to the same battery, that they so happen to be connected to the same battery. This is how we need to understand the parallel connections. So these are two independent circuits, and they just happen to be connected to the same battery. The same battery supplies both of them. Therefore, the battery does double the job that it does when it has only one bulb connected. And each bulb here will glow as if it was all by itself connected to the same battery. Like this bulb here, for example, will glow exactly the same like this bulb here, which is connected the only one connected to this across this battery. So here we have two bulbs connected across the same battery. The battery supplies two circuits, two independent circuits. So each one has its own current, which is I. Each of these independent circuits has its own current I. And if the bulbs are identical, obviously this current is expected to be exactly the same current. And it's exactly the same current as where the bulb is connected all by itself to this battery, the circuit A. So the bulbs B1 and B2 glow with the same brightness because they're two independent circuits and glow with a brightness that they would glow up there where the bulb is alone. And I hope you understand this. Does it make sense? This is how we must understand the parallel connections. And those two circuits work in parallel. And perhaps that's the reason why these two are called in parallel, not because we draw them in parallel. Okay, it's not a matter of drawing, it's a matter of how they work in their connections. So we have two circuits working together, working in parallel. So this is how we need to understand this. So here, for example, we have two loops, in other words, connected to the same battery. Here is one loop, the outer loop. The outer loop that includes B2 and the battery. And then we have this other loop that contains the bulb B1 and the battery. Okay. And if you don't believe me, actually, you know what I've done? I have brought some bulbs, real bulbs. Look at their brightness and let us see if I can make it work here. I have to move a few items. All right. Okay. So let me bring this thing down. I wonder if you can see well. Let me see how. I hope you can see those bulbs. Now, I want you to see that these two bulbs are connected in parallel in this arrangement. So let me connect the battery across both of them. Sorry. Now that the two bulbs are connected to the battery, they glow. They are supposed to be identical bulbs, as identical as they can be from the manufacturer. And now, if I remove one, in other words, I connect just one bulb to the battery. So to remove them, I can unscrew, I can unscrew one. So you see this one went off now, and only this bulb glows. You see, it did not affect actually the brightness of this bulb that remains there, because this bulb is connected to the battery, the same battery. Here's the battery, with its own independent kind of loop from the other bulb. So there is not a difference, especially if our batteries are new and they are good quality. There is no difference in the brightness of the bulbs, whether I have one or two in series or three in series, because then the more not in series, in parallel. Because the more bulbs I connect in parallel, it's like having extra independent circuits connected to the same battery. So they are not affected. So can you see that the two bulbs glow with the same brightness, whether they're one or two connected? I hope you can see that clearly. And this tells me that the one bulb, whatever happens to one bulb, if the one bulb goes off, it does not affect the other bulb. And it makes sense. I'm sure you know by now at this level that at home, for example, the connections of our devices, our lights, and everything, the plugs and so on, everything is connected in parallel. Why? Because when we switch on and off one device, we don't want it to affect the other devices, isn't it? That is why everything is in parallel in the home connections. So here was the parallel connection. I want you to see now, I have made another arrangement here. I have bulbs in series here. It's not very clear. Yeah. Here, the first bulb is just I want you to see the brightness of one bulb by itself. Okay. Now I'm going to change the circuit, and I'm going to connect the battery to a circuit, this second circuit, the second row, which is a circuit that connects only two bulbs, identical bulbs. Okay. So let me connect the two bulbs. Now watch this circuit. I'm going to make a circuit that contains these two bulbs and the battery. I just want you to see the brightness now of the two bulbs in series. Can you see the brightness, the difference in brightness? It glows so much dimmer now when we have two connected in series. Hope you can see that. They glow a lot dimmer than having one by itself. Let me connect this to one again to see the difference. Hey. You see that this one is brighter. One is by itself, it's quite bright, but then when we connect the second one in series, the brightness drops quite drastically. Now, if I connect three of them in series, now I have a circuit with three in series. Let me make the connection properly. The brightness drops so much. I don't know if you can see it clearly. It just, I can see the filament just glowing a little bit. So every time I connect an extra one in series, the brightness drops a lot. I mean, considerably, visible, a very visible drop in the brightness. I just hope that you could see that, because this lights here is not too ideal for experiments. And this is when we have two of them, they glow a little bit brighter if they are two. And then if it's just one, it glows a lot brighter. Can you see that? Can you see the difference in brightness under this lighting here? So now that you have an idea of how the brightness changes, let us fix this. Okay. Hope it's not very crooked. And let us go back to our worksheet again. Yeah. And where are we now? Just remember now the parallel connections that can be tricky to understand. But if you understand the parallel connections as separate loops, independent loops that are connected to the same battery, then you are much less likely to make a mistake when you need to predict of what's happening in the parallel connection. So now that we got an idea of the brightness of the bulbs in the different connections, let us try to explain all this. You know, when we have a circuit, generally, we need to understand what is happening in the circuit in terms of the current in the circuit, or in terms of the potential differences involved in the circuit, or in terms of the resistance that is involved in the circuit, or the energy, and so on. So we need to be able to become flexible to understand what happens to each and every one of those concepts in a circuit in order to see their role in the behavior of the different devices and components of the circuit. So let's start with the currents, which I believe it's easier to start with the currents. Let us compare currents here and see what differences happen with the currents in these three circuits. So the question C here says, compare the currents I, that means this is the I in circuit A, and this current in the series connection. So we need to compare the current in the single bulb and the current in the series connection. Let's compare this current and this current. Well, compare. What can we say? We saw that when we connect a second bulb in series, when we have two bulbs connected in series, the brightness drops quite drastically from the brightness of the single bulb alone connected to the battery. Just the brightness alone tells us that the current must be less. I mean, the brightness of the bulbs represent what the magnitude of the current. And we should expect the current here to be less. Okay, we saw that the brightness was dropped here considerably, which means the current is a lot less than the current here. But because these bulbs are identical, we can say that the current here is half of the current in circuit A. So if we compare the currents I and I series, the current in the series connection, in the series, is actually half of the current, of this current in the single bulb alone. And we should expect a smaller current. Why? Because we have double the resistance. It's double the battery in the path of the charge that moves inside this loop with double the resistance than this one, isn't it? Double the bulbs, double the bother to the current. So the current, in other words, the charge here flows a lot slower than the charge there, the charge that flows in the first circuit. And how do we need to understand the current in a circuit? Unfortunately, our books keep on insisting, saying that the current comes from the battery and moves and goes through one side of the bulb and comes out from the other. No, this is a very, very wrong way to understand the current in a circuit. The current, first of all, does not move in a circuit because current is not something that moves. It's a rate of flow. It means how fast the charge flows. And second, the current does not come out of any battery. Nothing comes out of the battery. The battery is like, we need to understand the circuit like a big wheel, like a bicycle wheel, whatever, where we move with one hand and we make it move all around. So once we push the wheel with one hand at one point, the whole wheel starts turning. This is how we need to understand what happens to the current in a circuit. Once the circuit is closed, the current starts immediately at all points in the circuit. It does not come from one point and there's nothing on the other side. The current exists immediately, starts immediately at all points in a circuit. So when we close it, there is a current there, there is a current there, there's a current there, to the left and to the right of the battery or the bulbs, everywhere. So we need to understand the circuit like a big wheel. Once we set it in motion, it moves, all the parts of the wheel move at the same time. If there are some obstacles here and there that obstruct the movement of the wheel, the whole wheel slows down. It's not one part of the wheel only. The whole wheel slows down. So once we have two obstacles here, which are the resistors, the whole flow of charge in the circuit slows down. So slower flow means smaller current. So that is why this current here in the series circuit is smaller than the current there. It goes with half the speed, we could say. The charge flows with half the speed. So this current is half. And please write comments whether you understand or not, whether you agree, whether you need more clarification. Okay. On the other hand, now let's say compare now the currents I and the one in the parallel connection, this current here. Now remember how we are going to see the parallel connection, like having two circuits connected to the same battery. So we have one current for the circuit here of this loop that contains the bulb B1, and then we have another current, the same current, that contains the bulb B2. And here we have an extra current, a second current. But both the current in this first loop and the other loop, each of these currents are equal to the current that is in the single bulb. it should make sense, isn't it? If this current is I, then we have one I for this bulb and another I for the bulb B2. So the total current, it's actually double this current. It's two currents together. So this I total here in the parallel connection is actually two times, two currents of this I. Okay, and of course, if we go here where we have the bulbs by themselves, in this branch and this branch, this current in bulb B1 is equal, so current I1 in bulb B1, that means is equal to this current I, and the current I2 here, which is in the bulb B2, this current I2 is equal again to I. And that is why if we add this together, the total current here, the current that is in the battery, in the main branch, is two times the current. And if we had a third bulb connected in parallel, the total current here would be three times I, because every time we add something in parallel, we make somehow we create a new current in a new loop. So this total current in the main branch is the sum of all the currents in the separate devices that are connected in parallel. And that is why at home it's not a good idea to connect too many things in the same plug, or because every time we connect a new device in the same plug, we connect it in parallel and draws its own current. And one current for this device, another current for another device which is connected to the same plug, and another current that's connected again to the same plug. I mean, the total current increases and increases and eventually becomes so much that it heats up the wires that are behind the plug, now behind the wall, that is, and they heat them up. And if there was not for a fuse, I mean, they could start a fire. It can become quite hot. The wires can become quite hot with big currents because of energy loss. I mean, the energy dissipates and warms up the wires because of the resistance of the wire. So do these things make sense? Tell me with a yes or no. This is very important to understand this total current in the parallel connection. So remember that the total current is the sum of the individual currents in the devices in parallel, and these currents are actually the same as this current there. Good. Now, we have enough with currents. Let's compare something else now. We had enough about currents. Oh, let's do this question. The last one is a nice question. Look at this now. In which of the circuits, A, B, and C, will the battery last the longest? In which circuits will the battery last the longest? That's a very nice question, actually. How can we explain this with the currents? Well, obviously, the battery that will last the longest is the battery that transfers energy at the slowest rate, isn't it? And which battery transfers current at the slowest rate? It's where the current is the smallest. And it is this circuit here, the series circuit, that has the smallest current. This current, which we call series, in the series circuit, this is the smallest current, which means that the flow of charge here is the slowest. It's slower than this one, where we only have one single bulb because there's only one resistance there. And here we have two currents. Obviously, we have two of these currents, two of this type of current. So here, this battery, first of all, supplies two circuits with current I, each one. And so this battery will be the first to become flat, isn't it? And then it will be followed by this one. And the last one, the last battery to go flat, is this battery that supplies the series connection, because here the current is the smallest. I mean, the smallest current means that the energy transfers slower in this circuit, because the charge moves slow here. So since the energy from the battery transfers slower, this battery in this circuit will last the longest. Do we understand that? Does it make sense? It's a tricky question, because many people think that this battery will last the longest because it has only one bulb. Nonsense. This is the battery that will last the longest because it supplies two bulbs in series, and the current in this circuit is very small because the flow of charge is slow there. Good. Now, I think this discussion is very valuable, even though it seems very simple. It is not simple. It is very, very profound ideas that are involved here. It's the way that we need to understand the circuits and their connections. Okay. All right. Now, let us compare now potential differences. Let's see what happens with the potential differences. What is this? Question H now. It says, compare the potential difference across bulb B1 in circuits A and B. Okay, so we need to compare this potential difference across B1 in this circuit and across this circuit, this V1, let's call it. Well, here obviously the potential difference across B1 is equal to the potential difference across the battery. For simplicity, we assume no internal resistance. Okay, so V1 actually is V here. But here now, this in this circuit, the battery supplies two devices. The potential difference supplied to the external circuit is split between two identical bulbs, which means this V1 and this V2 are actually each of these potential differences is half of this total potential difference, which is actually the EMF of the battery. So obviously, if we compare these potential differences, this potential difference is half of this potential difference in the first circuit. And compare the potential difference now in circuits A and C. Now obviously these two bulbs now, they both have a potential difference equal to the potential difference V supplied by the battery, because remember, each of these bulbs is connected to the same battery independently. This is the meaning of the parallel connection. So the potential difference across B1 is also V, like this one, the same, equal, and also across B2. In which of the circuits A, B, or C is the battery transferring more energy per unit time? Oh, in which circuits is the battery transferring more energy per unit time? Explain in terms of potential difference. So where can this be? Well, here the battery supplies a potential difference to this bulb. Here the source supplies the same potential difference across two bulbs. All this from one side to the other is V, like this V, like the EMF. But here, this battery supplies two potential differences, one for B2 and one for B1. So in this circuit, the battery, wait a minute, the battery, obviously here the battery supplies two circuits. So it transfers double the energy than this battery here that transfers only to B1. This one supplies energy to both circuits. This battery here supplies energy only to one circuit. So this one supplies two circuits. And therefore, this battery here transfers more energy. And of course, this battery will go flat faster than this one, isn't it? In half the time, actually, because it supplies two circuits. It does double the job. Okay, compare the resistance now. The next one, compare the resistance. If the resistance of each bulb is R, what is the resistance in circuits B and C? Well, if this bulb has a resistance R, what can be the resistance here? Well, we have two bulbs in series. That should be twice the resistance. So the resistance of this circuit is double. But the resistance of the parallel connection, it's, remember that each one has, in each loop, there's a current I for one loop and another I for the other loop. And when I say I mean this I here, same magnitude of current, same value of current. So what they want to say, which means now altogether, if we put these ones in this configuration where in this main branch we have double the current, it's like as if this current is double because it supplies like half the resistance of this circuit. So here the resistance is actually 1/2 of R, or R over 2. So the difference in resistance between the three circuits is quite big, quite significant. Here it's R, this is double, and this is only half of this resistance. And okay, oh dear, it's 12 o'clock. All right, so we had enough with this comparison, and I hope it makes a lot of sense. And I hope you believe me on the way that we need to understand and imagine what happens in the circuits if we want to make correct predictions in more complex circuits later on, in more complex problems. Okay, so we need to stop here. And okay, stop share. And next week I want us to see how to analyze a very complex series parallel network, a method, like a strategy of how to remove the complexity of things that look very complex. Okay, so let us call it a day, and see you next week. Be good, keep well, guys.